We are inside building 1 of the neutral beam test facility for ITER, which houses the complete one-to-one copy of the whole neutral beam injector for ITER, Mythica, and also the facility which is SPIDER, the most powerful negative ion source in the world, hosted inside this concrete bioshield. As you can see, SPIDER is completely inside a vacuum vessel, and this is because it should operate with hydrogen and with pure hydrogen, and at a very low pressure. So the whole vessel is evacuated, and then it is filled with a small amount of hydrogen, which is the operating gas.
Here we are inside SPIDER vacuum vessel, and I am in vacuum. This is the SPIDER source side, which is completely closed for electrostatic freezing.
And on the rear side we can see the cooling pipes coming from the bottom towards the source in order to remove 5 megawatt of heat from it. And we can see the radio frequency circuits, including the capacitors, the radio frequency drivers, and the coaxial cables, which are these big copper pipes here. This is an endoscope by which we can observe the inside of the source, and I put it in now. So we see the back side of the driver through which we enter in order to observe the inside, and also all those apertures which are the plasma grid which surrounds the ion source plasma. How do we create a plasma discharge? First of all, we inject hydrogen gas into the ion source, the blue molecules. These are hit by electrons and are dissociated, turning into 2 single particles, or ionized, they become red. And these ions and the neutrals move around, and particularly they can hit the plasma grid, where they are turned into negative ions, which go through the apertures located on the plasma grid, and are accelerated by the set of 3 grids, plasma grid, extraction grid, and grounded grid, until they go out of the accelerator. The grids are made of copper, and the particles coming from the ion source go through them, are accelerated, and they make a beam. Actually, a small beam, a beamlet. And there is 1280 of these small beams, which create the overall beam that goes out of the accelerator and deposits heat onto the surface of the calorimeter. But we also have another calorimeter, which is actually a diagnostic system. We call it Strike, and it is used to intercept the beam. We close it so that the beam deposits heat onto its front surface, and it is made of a particular material so that we can see on the rear side the exact pattern deposited on the front side by the beam. Here you can see what we expect to observe by infrared camera at different distances from the accelerator. And now from the photos of the system to the data which are produced. Particularly, the plasma emits light, and this light, as we see here, increases with the pressure and also with the RF power that generates the plasma. And the same is true also for specific lines emitted by hydrogen atoms. But if we take pairs of these lines and we compute the ratio between them, we can have indications about the electron density of our plasma. Again, this increases both with the RF power and with the pressure. And now we can have a look at the real plasma pulse. First of all, we start the emission of electrons, and then we apply the RF power, the red curve. When the RF power is sufficient, the plasma starts, the green curve. And we can also measure electrical signals like the blue curve, which corresponds to the current flowing through the plasma. And after 10 seconds, in this case, we stop the discharge. And here is what we expect to see in the beamlet. So the beam features will change as a function of the experimental conditions. Here is the same image in false colors, so we can easily see that the beamlet size changes when we apply different acceleration voltages. So what are we going to do? First of all, we will continue the investigation of the source properties. Particularly, we would like to increase as much as possible the radio frequency power. And simultaneously, we will explore the beam features in different experimental conditions. So we will see how the optics is, and we will look for the best experimental conditions, striving to obtain the goals set by ITER.